To Maths 306. We're now in the second chapter, and we'll be considering the topic direct products. Now, you had seen direct products in Maths 103. A similar definition will be used here, but in the context of a group, not a set. So we'll be considering direct products, direct product of any finite group of groups, and direct factors, and also we'll consider a theorem 2.4 precisely. So let's go ahead. Now, the first definition you need to know is what we call the direct product. And like I said earlier, basically we're using the definition from your 103 for direct products, but now we're considering it under the set of under groups, okay? So the direct product of two groups, J and K, is defined by this product, J cross K, such that you have two tuples, right? You could have A, B if you're multiplying A cross B, okay? So it takes this form. In our case, we have J cross K, right? So with the small letter J from the capital letter J and the small letter K from the capital letter K, which is written here mathematically expressed as this, okay? And it has coordinate multiplications in the sense that when you want to multiply two elements from this direct product, elements of this form, note this J1 is from capital J and K1 is from capital K, J2 is from capital J and K2 from capital K. So when you want to multiply them, we use coordinate multiplications to get their values when you're multiplying elements in this particular set or group, okay? So we have this as a relationship. The next definition you need to know is what we call a direct factor. This word, direct factor. So what's a direct factor? A normal subgroup, J, so it must be a normal subgroup of a group, is called a direct factor of G if there exists a normal subgroup K such that J cross K exists, okay? So once you have this relationship, we say that J is a direct factor of G, okay? You can check your lecture notes for more information on that. The next you need to know is what we call the direct product of any finite subgroups. So if you have a finite number of subgroups, say A1 all the way to AN, and you're told to define its direct product, it is simply the product of this form with group multiplication carried out component-wise as this, okay? So the elements, in this particular case here, is defined for elements in A and B, okay? When we have elements in A cross B, we're stemming from A1 all the way to AN, okay? So that's what we call a direct product of a finite number of groups, okay? Working with direct products, we usually identify single subgroups or groups, say J. If you have a J, just a single one, how would you write it as a direct product? Basically, it's multiplying, it's taking the direct product with itself, right? So we always represent it this way, meaning that there's nothing but one, it's multiplying with one, more like J cross 1, right? So the elements will just be elements of the form J cross 1, right? So that's what we have here. So whenever you have a single group and want to represent it in a direct product form, if you had A, for instance, it will simply be equal to the set A, comma 1, okay, with A from the capital A. That's all, okay? So that's how we represent single subgroups in form of direct products, okay? The next thing you need to know is what we call a projection mapping. What is a projection mapping? So projection mapping is a mapping of this form. What pi1 is doing, it's taking the element JK. You know where JK is from? It's actually from this set here. It's a set of from the set of direct product, right? That's where JK, the element from here. Look at it. If you pick anyone from there, so we picked 1. So now pi 1 is what it's taking is a map, and it's called a projection mapping. If it satisfies this condition, whenever it takes jk, it takes it just to j alone as a homomorphism from j cross k to j. Then we have a projection mapping pi 1. The other projection mapping is pi 2. This one now, it takes this jk and takes it only to k, and it's called a homomorphism from j cross k to k. Note, the first one is j cross k to j, and the second one is j cross k to k. Now, I want you to note something carefully. In the map pi 1, did you notice that j was mapped to j? Where was k mapped to? Clearly, you will say it went to 0, right? Meaning it went to the identity, because it went to 1. That's why it's not there. It didn't just disappear. It went to 1, the identity. Now, do you remember the definition of a kernel of theta? We say it's a set that collects all identities, all terms that are mapped to 1, right? Okay, so it means that if I want to find the kernel of pi 1, it will be all the elements k, right? Because k is mapped to where? To the identity in this case, because we're not seeing it there, right? Okay, because you remember that j as a single, as a subgroup is represented, let me clean this, you'll see it here. Oops, sorry. So remember now that j is represented this way, right? And there's only one here. If there's one beside it, clearly k must have been mapped to 1. So if k is mapped to 1, and 1 is the identity of our map pi 1, it means that the kernel of pi 1 is going to be k. Okay? There's one property we learned earlier in our last video, and that is that the kernel of theta is a subgroup of G, remember? And you also were able to prove that the kernel of theta is what? Normal in G. Do you remember that? We need that knowledge as we go along in this lecture. Okay, so let's continue now. So we have, you know now what the kernel of pi 1 is. What then is the kernel of pi 2? Let's look at it carefully. So jk is mapped to k, meaning that k is mapped to what? Meaning that j is mapped to what? J is mapped to 1. So the kernel of pi 2 is going to be all the elements j, right? Okay, such that j, small letter j, pi 2 is mapped to 1. So that will be our kernel, okay? And we know clearly kernel of theta is normal, meaning that this kernel of pi 2 is also normal in our group G, okay? Or whichever group we are using. So remember those. So those are projection mappings, definition you need to know. The next thing you also need to know is that also from the second point, since, okay, so that was what I was explaining before. Since kj is mapped to j, it follows that the kernel of pi 1 is k. You note that because I was pointing out the fact that k is taken to the identity, so that's why the kernel is k. And for pi 2, the kernel definitely is j, because in this case j is taken to the identity. So that's just what I've been explaining all this while. Okay, so let's move forward. So we have a theorem before us, and the theorem is also in your lecture notes on the chapter 2. It says that let G be a group, and we have subgroups J, K in G. Then the following are equivalent. That is, 1 is equivalent to 2, 2 is equivalent to 3, and 3 is equivalent to 1. So these statements are equivalent. The first one says that whenever you have that G is a direct product of J cross K, then this must hold. J will be normal in G, K will be normal in G. The product JK will give us G, and the intersection of J and K will definitely be the identity. So, and the second one says that once you have this one, once you have this, then it must be true that J and K commute element-wise, and also that every element X of G is uniquely expressed in this form. Okay, and when that happens, then you have a direct product. Okay, so the direct product, I shouldn't have this statement here. This shouldn't be here, because this gives us this. So this part gives us this, not so direct like that. Okay, so you can check your lecture notes, the hard copy, and you'll see. So like I was saying, this shouldn't be here. It's the knowledge of this that gives you this. Okay, so let's continue. So we want to prove that I implies II. So I, what is I? Is saying we have a direct product. We want to show that this will hold. Okay, so that's what we want to do. So we want to show that J is normal, K is normal, the product JK will give us G, and the section of G and K will be the identity. So let's go on. Okay, so we want to show that 1 implies 2. Now I want us to look at something. Before now, we saw that there is something called how to write J itself. Is that not so? We also saw something called the projection mapping. And we saw that once this projection mappings happens, you have the kernels in K for pi 1 and the kernels in J for pi 2, right? Okay, and I made us remember that we know that the kernel of theta or whatever map is normal in G. Do we have that? Okay, so let's continue. So we want to show that we have a direct product. We want to show this happens. So the first thing we want to do is look at the projection mappings. So we got the projection mappings, pi 1 for JK on J, and such that pi 1 maps to J. We've got a projection mapping for pi 2 on K, and such that pi 2 maps this way. Is that not so? Now, with what I told you earlier on, it is clear that the kernel of pi 1 is K, right? See, because pi 1 is mapping G to small letter G, right? And K is not there, meaning it has gone to the identity. So the kernel is capital K. Okay, so we found for pi 1 the kernel. Now, by that lemma, so you need to state the lemma that allows us to show that the kernel of theta is normal in G. So by that lemma, the lemma that states that if we have a map theta, G to G prime, that's a homomorphism, a normal subgroup of G, then the kernel of theta is normal in G. So based on this lemma, it follows that the kernel of theta 1, kernel of pi 1, which is equal to K, is normal in G, meaning that we succeeded in showing that the kernel of theta, the kernel of pi 1, which is K, is normal in G. What were we supposed to show for? Again, in our proof, we were to show that J is normal in G and K is normal in G. So we succeeded in showing for that of K. Okay, so for J, what would you do? You would define your pi 2, right? And pi 2 is taking K, is taking K, is it J? Yeah, J. K is taking it to K, right? So clearly our kernel, your kernel of pi 2 will be equal to your capital G, right? But you know that kernel of theta, in our case, kernel of pi 2, you know is normal in G. Okay, this implies, what did you have there? You know kernel of pi 2, what's kernel of pi 2 is G now. So kernel of pi 2, which is equal to G, is what? Normal in G. So we found that proof. So let's see how I wrote it here in long term. So what I've shown in a similar way, using the same lemma, we get that the kernel of pi 2, which is equal to G, is normal in G, which is what I've shown you step by step. You first take the map, you know the kernel is this, and from the condition that that lemma, which makes us know that kernel of theta is normal in G, you have that, and so we have that kernel of pi 2, which is G, is normal in G. So that's how I got this long sentence here, this one here. Okay. Okay, so we succeeded in showing this part. We've shown for J, we've shown for K. What of this product? Okay, what does it look like? So let's see how we did that. Now, working with direct products, we usually identify single subgroups J as what and K as what. Okay, so if you remember, I had said something earlier that when we're working with subgroups, single ones, we write them as this, right? Okay, so let's go forward. So J would take this from right, and K would take this from right. So if I want to find my product, JK, how would it look like? Okay, so any element we pick in this product, we'll get that JK will be of this from right. Do you agree? If I want to get this JK, all I need to do is multiply this and this, okay? But what is this? This element is where? Is in J right here. And this element is in K. So it follows that G is equals to JK, as you can see there. Okay? Meaning, so let me take it slowly for you. So I can say, another way of doing this is just simply put JK. You know what J is already. It is J, 1. And you know what K is. It is what? 1, K. If you multiply this by the rule of direct product, if you remember, that's J times 1, which is J. J times 1. 1 times K. What you get? The final answer will be J, K. But this element is where? It's taken from this, right? So, which implies that G is same as JK. Okay, so that's what we've done on the screen there. There are various ways of solving this, improving it. Once you have an understanding, you can write yours so that I see. Okay, and so we've finished proving. Let's go through this. So we finished proving. This and this. We've done this. We're left with this, right? Because we want to show that 1 implies 2. Okay, so the last part of it. So now we want to show that J intersection K is equal to 1. Now, if you're going to pick elements from J intersection K, how would it look like? So let's say if we pick J, K in J intersection K, it must be that J and K will be in J, and J and K must be in K, right? Because of the definition of intersection, right? It's only on that condition. So if it is both these two elements are in K, the two elements are in K, in J and also in K, then it must be that both of them are equal to 1. Meaning that this JK is same as 1, 1, and it is lying in J intersection K. So if all of this is, every time we pick J and K in this, it will be that they are this, then clearly J intersection K must be the set 1 itself. So we've succeeded in showing that J is normal in G, K is normal in G, the product JK is equal to G, and J intersection K is just our 1, the set of containing 1, a singleton set with the element 1 as required. So we're through with the proof. Okay, so you can rewind and just go by it slowly and try solving it on your own too and see what you will get. Okay, so let's move forward because we've just succeeded in showing that 1 implies 2, right? We still have to show that 2 implies 3. Okay, I will be doing 2 implies 3. Your lecture note, you will see 3 implies 1. You need to go through that and make sure you understand. If you don't understand, again, ask question on the WhatsApp group. Okay, so now we want to show 2 implies 3. So we have this. We have this. We want to show that we'll get this. Meaning we want to show that once it is normal, this J and K normal, we have JK is equal to this, and the intersection is 1, then there will be something that commutes in the set, okay? Now, commutativity will require a trick, and the trick is simply going to be seen shortly. Once you have that trick, you've sorted your question. So for commutativity, you start with that trick. Now, whenever you're told to show something's unique, I remember in 203 I told you, whenever they say show something's unique, look for another one that is going to answer that name, okay? So if this was supposed to be the unique one, find another X with something similar, maybe with J1, K1, or whatever. Just make sure that you now show that the two of them are equal, okay? So a unique rule, I will show for commuting elements, and then for uniquely expressible, you want to pick another element or something you claim to be X and then show that both of them are the same. So let's go to the proof for 2 implies 3. So the unique rule I was saying, the secret I was saying, is to set C, or whatever letter you want to call it, to be this term here. You will see why. So we pick J, small letter J in capital J, small letter K in capital K, and we set our C to be this particular letter C. Now, we want to carefully studying the C. If I put my bracket here and here, what happens? Let's see. Since J is normal in G, because it is normal, remember what we said about something being normal? We said that H is normal in G if and only if the right coset equals to the, left coset equals to the right coset, meaning that mathematically I can say GH inverse, what, is equal to H, right? You seen that? So I could do this. So because of this argument and the G all around it, you can say I can do what I'm seeing on the screen. So let's see how I used that knowledge to work. Okay, so because I know that J is normal in G, I carefully put my bracket in such a way that the J becomes the one multiplying the other term, this J. Can you see that? So J is multiplying this term. So which means that this element lies in J because it is normal. Remember? You saw how I ended my analogy of the inverse. We said it was equal to H, meaning that though there is G wrapped around everything here, it actually lies in capital H. So better still, small letter H will be here because it's an element, right? So it means that this would be, but there's G everywhere, right? But because it is normal, it can do that, okay? Okay, so let's continue. So J is outside now because the fact it is normal, and so we've succeeded in showing that this term with this my key secret here lies in J. Again, because K is normal, because that's property we have that J is normal, K is normal, we have that JK is a product, and that J intersection K is the identity, right? So now we know that K is normal. Again, I can quickly put my bracket here like this because it's normal. You see, K is multiplying everything here, so it follows that K inverse of this term lies in K. Hey everybody, this C is lying in J. The same C is in K. What does that tell us? Clearly that C lies in J intersection K, and it is in 1. Why is it J intersection K? Because already we know that J intersection K is the same as the set with just the singleton set with 1 in it, right? Okay, so that's why we're able to know that. Otherwise, if we didn't know what J intersection K was, C wouldn't be in it. But we know that J intersection K is a singleton set with 1 in it, okay? Because this thing C in J and at the same time in K means that it lies in its intersection, right? Okay, so now we know that C lies in J intersection K, and everything J intersection K is just the identity 1. It means that C must be equal to 1, right? But what is C? Everyone knows that the secret C is this value here. So it implies that this secret C is equal to 1. Oh, okay. Remember our target. Our target was to show commutativity. So if this my secret C is equal to 1, what happens? So we just keep arranging it and multiplying to make sure that we can get that kg. kj equal to jk. So to show commutativity. So let's see how we do that on the screen. Okay, so on the screen, we know that this is equal to 1, which is from here. Okay, that's at C. So I multiply both sides by k on the left because I'm dealing with a group, right? So on the left hand side, right here, I multiply with k and k. So this would be like k multiply here with k, multiply here with k, right? So that you can see that k times k inverse right here goes to identity, so you're left with jk j inverse, and k times 1 is just simply our k, right? Okay, the next I want to show commutativity. Remember, I multiply both sides by j on the right. So now on the right, if I multiply here, I put j here, I put j here. You see that? So this goes to identity, and this remains as it is. So we've shown commutativity. So the elements commute. So we finished showing commutativity, the first part of that other equivalence. The second part we need to show is that it's uniquely expressible. And I remember I said, once you're told to show that something is uniquely expressible, what do? You find another name for it, is that? So let's look. So now we suppose that another name for it is j prime k prime. Okay, so meaning that we know we were given that x is what's equal to j k, right? So now we are giving it another name. So since it's the same thing, we've equated them here, right? So they're equal. That's what we're saying there. So if they are equal, which is what we have here, the same multiplication I did before, I just keep multiplying left, right. So I multiply on the left by j prime inverse because I want to show commutativity, or well, basically I want to show that they're the same, not commutativity. Commutativity was what we showed before. So I multiply both sides by j prime inverse. So it remains here, but over here becomes identity. That's why we're having it here, and here becomes k prime. And again, if I multiply both sides by k inverse, so k inverse, this goes to identity, and this remains. That's how we have this. Oh, watch, the j's are equal to the k's. Again, what does that tell you? Remember, for them to be equal, and we're dealing with elements from two unique subgroups, j and k, it means they must be the identity, right? Okay, so but j inverse lies in j prime inverse j lies in j, k prime k inverse lies in k. So, and we know they're equal, and therefore these two must lie in j intersection k. But j intersection k contains only the elements of with the identity 1, right? So therefore this must be equal to 1, and this must be equal to 1. So if this term is equal to 1 and this term is equal to 1, all I need to do is multiply this term both sides by, say, j prime inverse. So I'm coming. So I want to show that the equality, I think you've seen it already at this point, because I want this to show that the two of them are the same, that is j prime is same as j, and I want to show that k prime is same as k. So all you just do is multiply this side by j prime and j prime on this side, so you will get this one here. Okay, for this one, you multiply both sides by k, multiply by k here, multiply by k here, and then you get this relationship. Okay, so that's how we arrived at the quality of them both. So hence, every element x of g is uniquely expressible in this form. And in conclusion, we have succeeded in showing that k and j commute element wise, and every element x of g is uniquely expressible in this form as required. Okay, and that's that completes the proof for this theorem, and actually theorem 2.4. So like I said, you go through the notes and double check what we did for 3 implies 1. I need you to be able to prove that too. Again, questions, ask on the WhatsApp group. Thank you.